Hi everyone, good afternoon. First of all, I would like to welcome all of you for attending today's webinar on optimizing design workflow using Solid Edge. My name is Wei Jie, presenter for today. I'm currently holding a role as a technical specialist at ACAD since 2013. And together, I'm also representing ACAD Solution, which is based in Malaysia. As for responsibility-wise, I'm actually providing things like pre-sales and post-sales support, doing software demonstrations, hosting of events like today, as well as providing technical advices to company on software solutions that can improve their workflows. So now let's take a look at today's agenda. Okay, so first I will be going through a bit on the profile of ACAD, followed by going through the design challenges that 3D CAD users are facing, followed by looking at the Solid Edge solutions available at the moment. We will also be doing a comparison between the different approaches available to CAD users when it comes to 3D modeling. And then I will highlight the pros and cons along the way as well. Followed by software demonstrations on how Solid Edge can help us to fight off those design challenges. And then I'll summarize everything and then I will conclude everything with a Q&A session after that. Okay, so a bit of information on ACAD. So ACAD Private Limited has been set up in year 2011, and along the way, we actually meet certain milestone. One of it is we actually brought in quite a number of different software CAD/CAM solutions, as well as setting up a training center with a group of professional trainers to provide quality support as well as trainings to all our customers. Okay, so now let's take a look at the problems and challenges that our customer and some of the 3D CAD users out there are facing. So this survey is done in year 2016. And then if you take a look at the table over here, you can see that some of the problem being highlighted is how quickly can they get that initial design created based on the limited information they normally get during the early stages. Next will be the ability to be able to reuse existing design, because you will not want to spend time to recreate design that is already created before. And the next one will be late stage design changes, which is also being reported as one of the major issue that they encounter. And then last but not least will be the ability to be able to import and manage their foreign 3D data efficiently. Okay, so it brings us to the solution for the challenges that we are facing. So we are actually finding solutions to help us to accelerate our design creation, performing faster revisions, as well as better reuse of our existing designs. Over here, you can see the portfolio of the solutions that Solid Edge provides. So the first one you can see under mechanical design. With the underlying synchronous technology working at the back end, you can design actually faster with a better workflow. And then on top of that, we also have electrical design. As you'll notice, there is now a greater demand for electrical design to be incorporated into your mechanical workflow. So in this area, Solid Edge provides solutions where designer can actually bring information that they have captured in their electrical schematic diagram into their 3D CAD environment and connects all of them together. So once your design is completed, the next logical step will be going to the simulation stage, where you need to test and validate your design according to the real world conditions. Solid Edge provides simulation solutions such as motion, stress, finite element analysis, and some other analysis as well that you can perform before we bring the product to the market. right? This can actually help us to reduce the number of prototype as well. So this will also lead to, after we finish the testing and validate that the design is working as what we expect, then this will bring us to the next stage, which is manufacturing. So over here, Solid Edge do provide solutions in two different manufacturing processes. The first one will be additive process, which is also known as 3D printing. And then the other process will be subtractive process, where Solid Edge has various CAM solutions for this stage as well. So once we have manufactured the product that we want, the next step will be so-called creating the technical publication in the form of product brochures, as well as things like installation manuals. So in Solid Edge, we do have tools that allow us to create interactive, high-quality documents that will update if there is any design change made to it. So after all these different stages, the 5 stages before that, you definitely have a lot of data, be it mechanical data, electrical data, simulation results. All these need to be stored somewhere and must be easily located and secure. So data management tool is also available for Solid Edge to ensure that the integrity, traceability, and efficiency of the data are being maintained. Last but not least, we'll be talking about cloud collaboration. It actually allows the user to share and collaborate design information, be it internally within ourselves, for example, between marketing team, technical, or your sales team. Or you can also collaborate externally with your suppliers, customers, or vendors. Right, so over here, we will do a comparison between the 3 different approaches being used by 3D CAD tools with regards to 3D modeling. So the first one we have over here is history-based approach, or we can also call it history-based modeling, where design is created based on features, after features, and then in order to create all these features, right, most of the time we will be creating or we'll be spending time on 2D sketches together with putting in all the 2D constraints like dimensions to help us to define the size and the shape of the design we need. So the benefit of this approach will be that it is dimension driven, right? So where we can actually change the geometry by editing the dimensions in the sketches. It is also highly automated. For example, when we edit the dimension of a feature, most of the time it will automatically change the dimension of other features as well, based on how we create the relationship between all these features. It is also feature-based because there is intelligence built into the features. For example, a hole is not simply just a hole. It can contain information like whether it's a counterbore or countersunk hole, whether is there any thread applied to the hole, and things like that. All these are good provided you have proper pre-planning of how you're going to create your model. This will also bring us to the disadvantage of this approach, which is it requires a lot of pre-planning for this history-based modeling approach. Think along the line, for example, when you create something, most of the time you will not know how your final design will look like, and also what features will be created first or in any particular order. And then this leads us to the second disadvantage, which is inflexibility. Okay, so for example, when it comes to design changes, your design is not created in such a way that, let's say your design is not created in such a way that the required dimensions are created for this particular change, or the order of the feature creation don't really allow for such changes to happen, then most likely your edits will result in a lot of failures. So as this approach is very much feature-based, the more features you have in a design, it will actually result in a larger file because every feature contains information or intelligence. This will also bring us to the last disadvantage, which is it actually scales poorly on many feature parts. it's not uncommon to have a part with a few hundred of features. For example, if you need to make a design change to one of the feature, most of the time it will affect other features as well. So this will require the system to recompute the model, starting all the way from the first feature, all the way to the last feature of the model. And then this will actually take a lot of time for the system to process. And then when we bring this part into the assembly, into a large assembly, this will take even more time for the system to process your model. So next we'll be talking about the second approach over here, which is direct modeling. So this method over here does not create feature. Okay, so if you need to build something, you can interact directly with the geometry of the model using push and pull action. What this means is that your editing of the model is very flexible because you don't have to worry about the order when creating features or pre-plan how you're going to create your model. As this approach does not create features, it scales very well on many feature parts. And next will be direct interaction. For example, let's say we need to edit the size of a particular area of a model. We just need to interact directly with this area and not afraid that this will affect the dimension of the other areas of the model. So next we'll be talking about the disadvantages of the second approach. Okay, because it's a featureless modeling approach, okay, and it also means that it doesn't contain a lot of information inside the model. For example, when you need to edit the holes, right, because it's not considered a feature and together with width dimension driven, when you need to change the size of, let's say, 100 holes from, like, let's say 10 mm to 20 mm, you will have to change them one by one. And this will bring us to the last disadvantage, which is little design automation. So because there's no information with regards to the holes, right? Because it's not recognized as a feature, so changing one hole does not automatically change the dimension of the holes in the model automatically. Okay, and then this will bring us to the last approach, which is synchronous technology that is unique for Siemens product. So over here, synchronous technology actually combines the benefit available in the previous two approaches together with some other benefits. So in synchronous technology, it is feature-based, and this means that there is intelligence in the model. It also allows for flexible editing and scale well because we are able to make direct edits without worrying about the order of the creation of the features or need intensive pre-planning. Over here, you will see 4 unique characteristics of synchronous technology available in Solid Edge, which is procedural features, 3D driving dimensions, phase relationship, and design intent. And all these I will cover more in details in the software demonstration. All right, so if it comes to the first demo over here, I will actually be showing you how to accelerate design in Solid Edge by creating an initial design faster and with more flexibility, as well as building in the design intent into the model at the same time. Okay, so let me go to my software. Right, so over here, I have already created a blank sheet metal part file. So over at this demo, you will notice a few things. All right, so I will be spending less time going to my ribbon to get all the commands at the top. In fact, I'll be spending a lot of time in editing and creating the geometry that I want by editing the model itself. Okay, so first thing I will be, as usual, I'll be beginning the creation of the model, starting with a sketch. Okay, so you notice that when I'm creating the sketch, right, I don't really put in a dimension for this sketch that I'm creating. Because normally during the initial stage, right, you're not given a lot of information. In fact, sometimes you don't even have the actual size of the model that you are creating. So Solid Edge gives you the flexibility of defining the dimension of your geometry initially, or you can actually put in the dimension in the later stage. Okay, so I'll just create a rectangle over here. And then once I created the 2D geometry of the shape of the sheet metal parts that I want, so next thing I will select the region. So once I click on the region, there's an arrow appearing on my region. So what do we need to do over here? Okay, so we just need to click on the arrow. Okay, so clicking on the arrow will allow me to create a thickness to that geometry, the 2D geometry. So I'll just put in the value for the thickness that I want, and then I will be able to create the base shape of my sheet metal parts. So the next thing that I'll be showing you is how to create flanges. So in history-based modeling approach, how we create flanges is we will be creating a 2D sketch first, and then using the 2D sketch, we will be creating the shape of the flanges. But in Solid Edge, we do it in a different manner. So we just need to select the side of the sheet metal parts here, and then you can see there's an arrow appearing. So clicking on the arrow, it will brings me the flanges. Okay, so I'll just create the flanges here, and then 2 further flanges on the side. So you can see I'm not really worrying about the dimension at this moment. And then next step, I'll be creating a cutout on the sheet metal part. So I'll be creating a geometry on the top of this surface. So you can see how easily I can actually create a cutout. So I just need to drag my mouse all the way from the left and to the right. And then straight away, I can create the cutout that I want. So the next thing, I will need to put in relationships as well as dimension to position and define the shape and position of my cutout. Okay, so I'll be putting 2D relationships and then together with the dimension. Okay, once I'm done with putting in all the relationships that I want, I'm ready to create the cutout. So I just need to select the 3 regions over here. And then at the same time, the arrow will appear on your profile. And then clicking on the arrow will allow you to create a cutout on your model. And then you can see at this moment, this profile that I've created is actually creating a cutout that divides my sheet metal part into half, which is not what I want. So I will just click on this button to apply the cutout to the unfold state of the sheet metal part. And then I'll just apply it. And then I'll get the cutout on my sheet metal. So one thing you'll notice that once I apply the cutout, you can see there's a blue color dimension appearing over here. So this dimension is actually applied to the 2D sketch that I used to create a cutout earlier on. So one thing that is done after I created a cutout, the 2D dimension has been converted into a 3D dimension. And then this 3D dimension will allow us to drive the shape of the cutout. So let's change the size of the cutout. So I just click on that. Sorry, so I change to 10. Okay, so you can see the size of the cutout has been changed from 12 to 10. Okay, next I will be creating flanges. So in this case, I will not be creating a full flange. I'll be creating partial flange. So creating the partial flange, you just need to click on this side of the sheet metal and then click on the arrow. And then this will give us the partial flange. Okay. Okay, now I'm given informations on the size of this partial flange that I'm creating. So I can now put in the 3D dimensions to help me to drive the shape of this partial flange. So I'll proceed to add in the dimensions. Okay, I'll set it to 30. And then over here, I'll set it to 20. Okay. So you can see as I put in the dimension and change the value, the shape changes as well. Okay, now I have another requirement, which is to move the flanges, the partial flange, to the center of this top surface. Okay, so this can be easily done by selecting this partial flange. So once you select the partial flange, right, you'll see the wheel appearing on the flange. So you just need to drag this wheel and then position it somewhere along the midpoint of this partial flange. And then after that, position it to the center point over here. Okay, and then you'll be able to see that this partial flange has been aligned to the middle point of that surface. Okay, next thing I'll be creating further features. So over here, I will start with a sketch on this surface of the partial flange. And then I will be creating a jog. Just by clicking this line and then clicking on the arrow, I can create a jog over here. Okay, so all these are good. And then I need to replicate this partial flange to the other side of the sheet metal part. So first thing, I will need to select the partial flange and then click on the mirror icon and then mirror it to the other side. Okay, so this will complete my initial design. But at this moment, I'm given some instructions that I need to make 2 edits to the sheet metal parts. Okay, one of it is I need to change the size of this particular part of the flange to be smaller. Okay, so in Solid Edge, all we need to do is to select this side of the sheet metal part, and then you can see the arrow appear on the screen. And then clicking on the arrow, it will allow me to edit the size of the shape here. But then you'll notice that when I'm editing this part here, this part is also changing as well. This is due to the design intent table, which is actually used to predict what is the intent of the user. So you can see the symmetric design intent option is turned on. So the system is actually predicting this particular face that you are editing is also trying to edit the symmetrical shape that is on the other side of the axis. So over here, the designer can actually tell the system whether they want this to be happen onto the model. So I want this to be this way. So I will just apply it and then reduce the size by 8 mm. And then this will complete the first edit. Okay, now I need to proceed with my second edit, which is to change the angle of this surface here by 10 degrees. But then I don't want the other side of the surface to change as well. Okay, so I just need to select this surface, move the wheel, and then I need to turn off the symmetric design intent. And then this will allow me to change the angle for this side only. And then I'll just type in 10. And then I have the second edit done in a very efficient manner. Okay, so this will complete my first part of my demo, which is on fast and flexible creation of a sheet metal part. Okay, next I will go to the second demo. Okay, the second demo, over here, there are 3 different parts that I'll be focusing on. The main thing is how fast we can make revision in Solid Edge. And then I'll be also showing you how we can actually simultaneously edit multiple parts in an assembly, how quickly we can respond to design changes, as well as how Solid Edge manage imported 3D CAD data. Okay, so let me go back to my application. Okay, so over here, you can see I have an assembly, and then on the left side over here, you can see I have a lot of sub-assembly as well as part in it. So what I'm trying to do over here is we will actually be looking at editing the width of the wheel, the size of the wheel over here. But then you'll notice that if we are going to edit the size of the wheel, it will definitely interfere with the bracket at the side over here as well. Because the bracket and the wheel is belonging to different parts, so in traditional method, it will be not so straightforward in how you go about editing it. So in Solid Edge, we can actually easily select the parts, select the surfaces of different parts easily, right? So just let me select the sides here. So I'm going to select the surface over here, this surface, and this surface as well. So the 4 surface that I select over here belongs to the wheel. And then this surface that I'm selecting is belonging to the bracket, right? So after selecting the surface that I want to edit, okay, I just need to click on the arrow on the wheel, and then this will allow me to change the size of the wheel together with the bracket together. And then I just need to type in the value that I want to increase, and then this will complete the edit. Okay, now after editing the size of the wheel together with the bracket, the bolt has been, the bolt we need to change as well, right? So I just need to select the bolt here, and then selecting the surface, then just drag it out by 20 mm. Okay, and then this will complete my changes to the wheel together with the bracket and the bolt. Okay, now after finishing the edits on my assembly, okay, let's say now I have a technical drawing of my trolley. You can see the dimension of everything over here is still follows the previous edition of the trolley before I make the changes. So over here, there is a quick way that we can straight away update the view. Let's say we have do some changes already, we can update the changes over here. So before that, let me save the file. Okay, after I save the file, I'll go back to the drawing, and then I can click on Drawing View Tracker. And then over here, there is some instruction given to me that I need to update the view because there is some design change made to my models. So I'll just close this, and then I'll click on the Update View button. And then over here, they will tell me that these are 2 things that has been changed, right? So I'll just clear it and close. And then you can see the model has been changed, the drawing, as well as the dimension is changed as well. Okay, so this means that all the part files, your assembly files, and your drawing files are all interlinked together. So any changes that you made in any different, any particular environment, all this will update to the relevant files as well. Okay, so this will be the first part of the faster revision demo. Okay, and then for the second demo, I will be editing this part. Okay, in fact, over here, I have a part that is done using history-based approach. And then over here on the left side, you can see I'm in the ordered mode. So in Solid Edge, we are not only given the choice of using synchronous technology to proceed with our editing. we can interchange between different approach at any point of time, right? Because there's still some advantage of using history-based modeling, right? So we have the flexibility of changing to any modeling technique at any point of time. So over here, there is 4 changes that needs to be made. Okay, the first changes. Okay, before that, let me take down the time that I spent changing using the history-based method, and then later on I'll compare the time that I took for changing in the history-based technique as compared to what I did using synchronous technology. Right. So the first thing that I'm changing, I'll need to change this depth of this pocket to be 75 mm deep. Right. So I'll just select this and then edit the definition. And then over here, I discovered that there's a dimension that allow me to change the depth of the cutout. So I'll just proceed and type in 75. Okay, so it changes as what I expected. So I'll just accept the changes. But then after I accepted the changes, right, it actually removed a lot of features away from this part of my model. So I need to undo it to get back the previous state. And then we need to take a look why this feature changes as well. So I'm going to examine this part of the feature. And then you'll discover there is a small little yellow dot appearing over here, which means that this surface over here, it actually relates to this surface. So if you change any of the surface, it will actually move together. So we need to remove away this relationship. So I will just proceed and do so. Okay, so after I'm done, I'll go back to this feature and then change the size of it to 75. Accept the changes and then okay. So now I have made the first change. I proceed to the second change, which is to align this surface. Okay, which is to align this particular surface over here that I'm pointing towards to with this surface. Okay, so let's take a look how it's done using history-based approach. So first, we will click on this feature and then take a look at the profile. Okay, one thing about history-based approach is that if let's say one feature is created before another feature, you will not have any references for you to refer to. So at the moment, we can't edit this profile, so I'll just close the sketch. Okay, and then let's take a look at this feature here, which is cutout 15. And then this feature that we are actually referring to is cutout 29. So what we'll need to do is we need to rearrange the order of the creation of the feature and make cutout 15 to be created after cutout 29. So I'm going to drag cutout 15 after cutout 29. Okay, after I did so, I will go back to this feature over here and edit the profile. Okay, so now you'll see that I have something to reference to for this profile after rearranging the order of the creation of the features. So let's proceed to align this line to this edge. But then when I proceed to align it, it tells me that there is some conflict with my relationship. So over here, I will need to relax some of the dimension. So I need to unlock the dimension over here, this one as well as the angle dimension. Okay, after relaxing all the dimensions that is required, I can now align this with this and then close the sketch. Okay, so it's done. So supposedly the second change has been done, but I'm not really sure that this surface has already aligned properly with the other surface. So we'll do some checks on it. So I'll just proceed to get my measure tool and then just do a measurement of these two surfaces, and then you can see that there's a difference of 2 degrees between the two selected surfaces, which means that they are not really aligned. Okay, so we need to do some check on this. So when you click on highlight on this surface, you can see there's a draft feature applied to this surface. So most likely it will be caused by this feature, which caused the misalignment of the surface. Right. So I'll just click on this, edit it, and I need to add this surface to the draft as well. You can see the draft angle is 2 degrees. So I just accept it. Okay, and then upon accepting the changes, you can see it affects my rounds as well. So I'll just click on my rounds and then add this edge back. Okay, so I'm done with the second change, and now I will proceed to make the third change over here. So the third change over here is to reduce the overall height of this fuel tank from its original height to 425 mm, 425 mm. So in this case, if you are not the original creator, sometimes you will find it hard to locate the features to edit, to get to the correct features in order to edit the things that you want. So let's proceed and just highlight on this surface. And then let's edit the profile. Okay, so once you open up the profile, right, you can see this sketch over here doesn't really allow us to edit the overall shape. So I'll just close this sketch. And then I'll go to the next one, cut out 6, and then edit the profile. Okay, so this looks like the appropriate profile that we can go about editing. So I'll just go and proceed with adding the dimension to allow me to edit the overall height of the model. Okay, 428, and then I need to change it from 428 to 425 and make it a driving dimension. But then I can't really change it to driving dimension because after examining the model, I find that there are some relationship created over here. So I just need to delete away the relationship. So upon doing so, I will try to type in the size that I want. And then now I can change the dimension. And then I will need to add further relationships to make this a parallel. After that, I will close the sketch. Okay, and then the third change has been done. But then if you look closely, you can see over at this surface, the round has been taken away. So I need to click on this feature, sorry, the rounds, and then add the rounds back over here and over here. Okay, so now after you finish editing, okay, we'll go to the last one, the last edit, which is to change the angle of this surface. This surface that I'm selecting, I need to add another 15 degrees to this surface here, right? So I'll just go to this surface and then look for the first feature that is created for this model, which is protrusion 1. I'll select that and then edit the definition. And then over here, you can see there's an angle dimension that I can change to increase the angle. So I'll just proceed to add a formula of plus 15. And then after adding in the 15 degree and accept it, and now you discover that the model doesn't generate properly. You can see a lot of feature has been removed, and if you look at the history tree on the left, you can see there are a lot of failures as well being introduced. Okay, so let's take a look at the time right now. So I actually took about 9 minutes and 32 seconds for the for change, but then for the last change, right? In fact, there are a lot of things needed to be sorted out. So I did not really finish the last change. So let's take it as 9 minutes 32 seconds for 4 changes. And then now let's take a look at how synchronous technology can help us to make all these 4 changes faster, right? So let me close this file, and then I will open the same file again. Okay, so in order to proceed with synchronous editing, first we need to move all the ordered feature to synchronous features, right? So I'll just proceed to select all the features over here and then move it to synchronous. Okay, upon doing so, I will be given a warning, and it's telling me that this particular feature called thin wall, it doesn't, it's not able to be moved to synchronous. All right, so I'll just cancel this, and then I just need to know where is the thin wall being created. So the thin wall, if I highlight over here, so basically this thin wall is to create, is to remove the materials inside this cylindrical opening, right? So later on, I just need to remember to apply this particular feature back, right? So I'll just proceed to delete away thin wall from my model, and then select all the features again and move them to synchronous. Okay. Upon doing so, I need to move my modeling mode to synchronous. Okay, so now I can proceed to do my editing on this model with the 4 changes. Okay, now I will start my watch. Okay, the first edit, I need to make this 75 mm deep. So what I will do is to just add a dimension, and then just type in 75 and then enter. Okay, and then this will complete the first edit. Okay, the second edit is to make these 2 surfaces to be aligned. So I just need to go to my 3D face relationship and make this surface to be coplanar with this surface. Okay, done. So we are done with the second change. Okay, now the third changes. The third change will be to edit the overall height of the fuel tank. So I just need to, in fact, when we transfer all the features from ordered to synchronous, the dimension is also port over as well. So I can go to my PMI, and then over here you can see there's an overall height dimension being transferred over as well. So we just need to click on this dimension, make it a driving, and then just type in 425. Okay, and this will change the overall height of my fuel tank. This completes the third change. And then last change will be to adjust the angle of this surface. So I just need to select this particular surface, move the wheel to this edge here. Okay, and then I just click on the wheel and then type in the angle that I want, which is -15. Okay, and then now I completed my 4th change. So let's take a look at the time span. Okay, so the time I spent for these 4 changes is just 2 minutes as compared to the 9 minutes and 32 seconds earlier on, which we did not even complete the very last change because there are a lot of failures introduced. right? So you can see that synchronous technology, it can actually help us to respond very quickly to design changes, right? Okay, now I'll move on to the last part of this faster revision demo. Okay, over here, I have a assembly with a base part and a motor part. And then all these parts are actually created in Solid Edge. And then later on, I'll bring a few parts into this assembly. And all the parts are actually created in some other CAD tools. And then in this case, we are using Inventor. Okay, so I'll just proceed to bring the foreign data in. So over here, you can have a look at what are the different file formats we can actually bring in to Solid Edge. So you can see there is AutoCAD file format, there's CATIA, there's IGS, Inventor, Pro-E, Step, and SolidWorks. All right. So for this example, I'll be importing Inventor files. So I'll just select Inventor, and then let's bring this file in. I'll select one template here. Okay, so once I imported the Inventor file in, you can see under the history tree over here, there isn't any information available other than the geometry. There is no dimension, nothing at all. Okay, so I'll show you how easy it is in Solid Edge that we can edit files that we import from other CAD tools. So let's say now I want to, we need to make some changes to the size of this surface. So just click on this surface, we'll bring out the arrow. And then by clicking on this arrow, okay, it will allow us to change the shape, the size of it. So I just want to increase the size by 1 mm. Okay, so this will let me proceed with my first edit. Okay, now I need to make this edge to be slightly smaller. So I will do this by using 3D dimension applied to this. Okay, make it a driving dimension, and then I'll make it 50 mm. So you can see the size changes as well. Okay, next we'll be making changes to this hole over here. So I can just simply click on the hole, right? You can see there will be one dimension appearing. So by changing dimension will allow me to change the size of the circular cutout as well. Okay, last but not least, we'll be making the change to the rounds. So I'll just select one of the round over here, and then clicking on the dimension will allow me to highlight all the rounds with the same size. So after that, I'll just type in 1.5 for the size that I want. And then this will allow me to change the size. Okay, after that, I will save the file. And then I'll go back to my assembly, and we are ready to bring in the parts that is converted from Inventor and bring it into this assembly. So I'll just go to my library, and then it's just a simple drag and drop, and then you have the part inside your assembly environment. And then now we are ready to align the part on the right to the part on the left side. So I'll be selecting this surface and mating it to this surface over here. And then align this axis to the axis of this cylindrical object. Okay, and then we are done. Okay, so after I align the parts to the assembly, now I need to make some changes. Okay, so we are given instruction on, we need to make this shape over here that I'm highlighting to be the same shape as the motor at the back. Okay, so if you are using traditional modeling approach, you will need to spend a bit of time to change your sketch to redefine the shape to be the same as your motor. But in this case, in Solid Edge, we can do it in a completely different manner. So I just need to activate this part. And then I just need to extrude this surface. Okay, and then extrude all the way to this top surface here. Okay, and then you can see the shape has been formed. And then I just need to apply my rounds back. And then this will complete my edits. Okay, so now I will bring in some other parts that is created from Inventor. So the first one will be the fan blade. So align this surface to this surface. And then this cutout to this cylindrical. Okay, so upon accepting, you can see that the other part has been accidentally positioned in a very weird manner. That's because after editing the shape, the relationship has been changed as well. So we just need to go back to the part over here. You can see there's one relationship that has been classified, there's an error on it. So I just need to go and edit this and then put it back to this part here. Okay, so now it's done. So for the last part over here, I will bring in the fan knob and then align this surface, and then here. Okay, done. Okay, so this is how easy we can actually bring in 3D CAD informations from other tools and bring it into Solid Edge. And then in the next example, I'll be showing you how to bring in 2D informations as well. So you can see over here, this is another Inventor part with no informations at all. Example, dimensions, right? Of course, if you want to make some edit, it's also quite simple. We just need to add in our 3D dimensions and then proceed with the editing. But let's say I have the 2D informations available to me already. So I can make use of the 2D informations and use the 2D data to drive the shape of my 3D, right? So I just proceed and open up my 2D data. So you can see there's a DWG file here. I'll just open that. And then over here, you can see I have a top view and a side view of my 3D model with the dimension already created appropriately, right? So I'll just proceed and create a 3D over here and then point it to the correct part file. And then this will allow me to actually port over all the dimensions. Oops, sorry. So let me do it again. Okay, so you can see now my sketch is already port over to my 3D model, and then I just need to use the wheel over here to readjust the position of my sketch to align it to the model. Okay, so I'm done with the alignment. Okay, so you can see the sketch has been attached to my 3D model. Okay, one thing you'll notice that after attaching the sketch to my model, the dimension is in brown color, which means that the dimension is not attached to the 3D geometry. So we need to right click on the dimension and then attach the PMI. And now it's showing blue color, which means that it's already attached to the 3D geometry. And we can now use it to drive the geometry. So example, I will click on this dimension here. You type in 2 mm, and then you can see the shape is changed as well based on the dimension. Okay, so we can also effectively use 2D information that is already available to help us to drive any edits that we want in our 3D models. Okay, so that will be the end of the second demo over here. So let me go back to the slide. Okay, the last demo I'll be showing you how easy it is to perform design reuse in Solid Edge. So it's as simple as just copy the feature or the parts from one model and use it in another design files. Right, so I'll just go back to my application, and then over here I have one model, just a very simple model. And then the things that I'm trying to reuse over here is the handle over here and the keyhole. These are two features that I want to reuse it. So we just need to window select the two features over here. You can see they are selected. And then move the wheel to the base of the handle over here. And then I'll just use Control C to copy the features. Okay, after that, I'll just go to the design file that I'll be reusing this feature that I've copied. And then I'll just paste it over to this file here. Okay, after that, I'll make use of the wheel to reposition the feature that I've copied over. Okay, so now I've properly aligned the two features onto the correct position that I want on my casing in this model. But then you can see the color is different from my base model because we haven't attached the feature that we have copied from another model into this file. So the last step, we just need to attach it. Okay, and this will complete my first part of my demo. So over here, I'm actually showing you how easy it is to actually reuse certain features from another design file and use it in another model. So over here, I have an assembly. You can see the feature that I've copied, the handle, the keyhole is already ported over. And then in this example, I'll be showing you how to reuse. Just now is reuse feature, but this time around I'll be showing you how to reuse parts in an assembly. Okay, so let's say I've already created similar parts that I want to use in this design. I can go to my library over here, and then I'll just drag and drop from the library. And then over here, I will have this push button. Okay, now I want you to take note how many steps I'm actually using to position this push button onto my assembly. So the first step, okay, I will be selecting this surface and then mate it to this surface. So there will be two steps. Select the axis of this push button, align it with the axis of this cutter. So total there will be 4 steps to complete the placement of my push button. Okay, now I will show you another method that can reduce the number of steps that I took just now into half. So what I will do is just select the part that I'm using to position just now, which is the push button, and then click on this command called capture fit. This will allow us to remember the relationship that we use for the part, and then when we drag similar parts in from the library, we just need to use 2 steps. So the first step is to select the surface here and then select the axis, and then we can actually place the push button correctly into the circular cutter. We can also drag and drop from the history tree over here. And then this will bring out the parts as well. And then using 2 steps, we can put in the push button as well. Right, so I'll bring one more. And this will complete this assembly. Okay, so you can see how Solid Edge can actually help us to easily reuse features as well as parts that we have already created beforehand and reuse it in future designs. Okay, so this will conclude my 3D demo. So now I will proceed to do a summary of what I've shown for the past hour. Okay, so the first benefit of Solid Edge with response to the design challenges that I mentioned earlier on, it allows us to actually easily edit 3D designs without the need to understand the design history or any pre-planning of the original design process. So that there's no need to pre-plan a lot ahead, but you can actually quickly come up with your initial design pretty fast. Original user design intent is automatically recognized and can be adjusted on the fly. Right? No more fail features after edits. You can easily, accurately edit geometry using simple push and pull actions. And then you can also edit your geometry by using 3D dimension, which is not available in other approaches. You can also edit multiple features or even multiple parts at the same time, and then technical drawing will update together with the changes that you made in your design as well. You can easily make use of designs or features that you have created before, and using simple copy, cut, and paste feature or drag and drop, you can bring the features from one model to another. And then last but not least, Solid Edge allows us to use both synchronous technology together with history-based technique for your workflow. If you have any inquiries, be it sales or technical aspects, you can contact us using the information on this page.